Hello everyone, welcome to JG Chemistry. Guys, in the previous video of NMR, we learned about DEPT technique of resonance carbon-13 NMR and proton decoupled carbon-13 NMR. If you have not seen that video, you can find the link of the video in the description box of this video. And if you want me to prepare any particular topic related to any organic chemistry topic or spectroscopy, you can write down in the comment section. I will surely make a video on it. In today's video, we are going to discuss about NOE, which is called a nuclear overhauser effect, two-dimensional NMR called correlation spectroscopy COSY, and CIDNP techniques. The topic is on demand, like many of you were asking for it, so I prepared a video on it. Hopefully you will get the benefit out of it. The topic is mostly useful for M.Sc chemistry students, and sometimes the question you can see in CSIR net and GIT examination. Let's begin. First, we will discuss the nuclear overhauser effect or enhancement called NOE. So what is NOE? We will see that normally we know that we have seen proton NMR and C13 NMR technique. There are two active NMR active nucleus. So basically here in this technique, when one of the two different types of atom will be irradiated, then we are going to record the NMR of one nucleus while the intensity of the non-irradiated will be enhanced. So we'll understand it better by taking one example. Before that, we will cover few logic or few points related to NOE. And this interaction is usually through space, not through bond like we have seen in proton NMR and C13 NMR. That interaction occurs through bond. But in case of NOE, the interaction is through space. This is a heteronuclear effect, means it occurs between carbon-13 and proton. We'll see that again. So basically, in a straightforward definition, you can see or example that on irradiating the protons, the carbon-13 signal intensity is enhanced. And this enhancement is called the nuclear overhauser effect. So we are irradiating the one set of nucleus, and the intensity of the other set of nucleus is going to enhanced. Then it is called NOE. And the order of the intensity, you can see it is high when you have more number of proton attached to that carbon, and it is going to decrease as the number of proton is going to decrease here. The condition is that the two nuclei should be very close to each other to exhibit NOE. Like the two nuclei means if you are irradiating a particular proton, then the intensity of the carbon is going to enhance, which is in the close proximity of this proton, which is going to irradiate it. Then only you will have NOE. So we'll see by taking this example of NN dimethyl formamide. You can see here the nitrogen is having lone pair of electrons. So you will be having here the conjugation between the lone pair of nitrogen and the pi electron of the carbonyl bond. So basically you will get a C double bond N characteristic here. So the rotation will be restricted here around this single bond. So we can see that the two methyls, then it becomes non-equivalent to each other because of the restricted rotation. So if it is non-equivalent, then how we can find out that? Now, in this case, you can find out if you want to assign the stereochemistry, that which methyl is syn to the aldehydic hydrogen and which methyl is anti to the aldehydic hydrogen. So that information, the three-dimensional representation or stereochemistry, we can assign by NOE. So let's see, we are irradiating the proton, the aldehydic proton, and we will see the effect of this irradiation on the signal of carbon of the methyl. So we have observed that the methyl group, which is anti to the proton or aldehydic proton, the NOE occurred around 31.1 ppm, while the methyl group, which is syn to the aldehydic hydrogen, the NOE occurred 36.2. So you can notice the methyl which is syn to the aldehydic, the NOE is high as compared to the anti. As we know that the NOE depends on the distance. So we can see that the aldehyde proton and the syn methyl is close to each other as compared to antimethyl. Therefore, the intensity of the NOE for syn methyl will be higher, and so you can assign that this particular methyl group is syn to the aldehydic hydrogen. And you can see the spectrum as well. Now you have three peaks, for two for methyl, one for aldehydic hydrogen here. On irradiation, this is a proton decoupled C13 NMR. On irradiation of this proton, this is going to disappear in the final output, and you can notice the enhancement in the intensity of the peak, which is more for CH3 of syn CH3 as compared to the anti-CH3. So this type of enhancement will tell you the correct stereochemistry or configuration of the molecule. And again, one more application of NOE that you can find out the structural elucidation and determination of stereochemistry. So let's take another example where you have the two methyl groups with respect to one hydrogen along the double bond. Now you need to find out out of two methyl, which methyl is cis to the hydrogen and which methyl is trans to the vinylic hydrogen. Two methyls are non-equivalent to each other, so it will give a separate peak in NMR. So now if you irradiate, let's say, the methyl which is cis to the vinylic proton, then we have observed that there is 17% enhancement in the NOE for the vinylic proton. While if you irradiate the trans methyl, then there is no enhancement in the proton signal. So that says on irradiation of the methyl which is not leading up any NOE, then it is a trans methyl, while the other methyl which is causing the 17% NOE after irradiation, we can assign that this methyl is cis to the vinylic proton, and so you can assign the stereochemistry. So you can see here again you are having the three peaks. On irradiation of the one methyl peak which is cis one, it will disappear and will cause the enhancement 7% intensity in the CH vinylic peak. While if you irradiate the other transmethyl, then you can see, and later on you can observe that there is no enhancement, and you can assign cis and trans respectively. So to assign the stereochemistry, this is another example where you can notice that the two isomers are very closely related, and if you notice the NMR of these two isomers, it is very close and it is really difficult to identify the two isomers. In that case, we take the help of NOE. How? If you irradiate, let's say, the OH proton, then it is definitely going to show some enhancement in the signal of CH3. While if you notice the other isomer, the OH is meta position to methyl group, so you may not see the same enhancement, or maybe very little enhancement is there or no enhancement in the NOE for this particular isomer, and then you can assign the correct stereochemistry and structure or configuration of the molecule, that the spectrum belongs to whether ortho disubstituted or it is a meta disubstituted. So in this way, NOE is going to help you to assign the correct stereochemistry of the molecule. So we have discussed about NOE. If you get this question related to NOE, you can take either of the example from here, mention the points, and you can explain it by drawing the plot also. Next is 2D NMR, which is two-dimensional NMR called correlational spectroscopy. We call COSY in short form. So what is that? We'll see here why we need 2D NMR, because normally we study one-dimensional NMR like proton NMR and C13 with respect to one axis, and usually we identify many molecules with respect to 1D, but some molecules where you have many diastereotopic protons or groups, the 1D NMR gets failed. It is really difficult to distinguish the diastereotopic proton which are having very closely related to chemical shift you cannot identify it, then we take the help of 2D NMR. So it uses a two frequency axis, and here you will be getting the diagonal peaks, and you will obviously get here off diagonal intensity peaks, which proves that there is a spin-spin coupling between the protons. So the off diagonal peaks tells us about the spin-spin coupling, and then we can tell that which proton is coupling to which other proton. And it is two types of COSY. One is homonuclear, other is heteronuclear COSY. Homo means both nucleus are same, proton proton, and hetero means two different nucleus called C13 and proton. We'll discuss first homonuclear COSY by taking a simplest example, ethanol, though we don't need any 2D for ethanol, but just for the explanation sake to understand it, we'll take this example. And this is how the two-dimensional NMR looks like. You have two axes here, two frequency axes on x-axis and y-axis. Since we are talking about homonuclear here, both nucleus are same. So on both the axes, you will be having proton NMR here. For ethanol, we assume 3 peaks in proton NMR, and you can see the splitting here. The splitting always occurs because of the number of neighboring protons plus 1. So you can see for this methyl, you have 2 protons plus 1, it is 3, then it is going to split as triplet. While for the CH2, you have 3 protons, then 3 plus 1 is 4, it is a quadrat. The OH proton will not couple with this CH2 because of the exchange, and so it doesn't exist here, and because of the exchange, and so it is going to show the signal as a singlet here. And you can notice with respect to the chemical shift, since the quadrat is attached to the electronegative atom, and we know the electronegative effect on the chemical shift, de-shielding occurs. Therefore, you have here a high del value for the quadrat as compared to the triplet, and then OH is, we know the range for alcoholic OH, accordingly it will appear. Now you can notice here you are having here diagonal peaks with respect to with respect to each signal. For CH3 below your CH2 and below your OH. On diagonally you have some area here, and with respect to this diagonal axis you have off diagonal cross peaks here, which is called contour. Then you can see you are having one contour C below CH2 and one contour is there just below triplet CH3. So since these two are getting here, we have to see now whether the two are coupling to each other. So if you draw an imaginary line from the diagonal peak A to the cross peak C, and similarly from this cross peak, if you lead down, go down, and it meets to the contour diagonal peak B, that says the A and B are coupling to each other. A and B means the CH3 and CH2 are neighbors and they are coupling to each other. Similarly, you can find here if you go from A to D and B to D, that it is showing the same D cross peak means A and B are coupling to each other, that is for CH3 and CH2, and so we can say that two nucleus are coupling to each other. So basically we need the we take the help of coupling by 2D NMR. So this is homonuclear. There is another example for heteronuclear, same ethanol will take. So you'll be having on x-axis C13 NMR, and on the y-axis you will be having the proton NMR. Since ethanol is having 2 carbons, so you are having 2 carbon signal, and below each carbon and the respectively proton CH3 carbon and CH3 protons, you can see if you meet A, there is a diagonal peak, cross peak, you can say A, and then again if you go down from CH2 carbon and the CH2 proton, it is meeting some area B, that says that this signal belongs to the CH2 and the previous one A belongs to CH3. So in that way you can assign that the set of proton belongs to respective carbon. Basically this heteronuclear COSY is based on the 1J CH coupling, the proton which are directly attached to the carbon. So based on 1J coupling, you will see the peaks here, and Here you can find the cross peaks which are directly connected to the respective neighbors. Here means that is carbon. Now we'll see the practical approach of this COSY by taking the actual example. We'll see metadinitrobenzene here. So if you see the metadinitrobenzene in one-dimensional proton NMR, you can see here 1, 2 and 3 signals for proton NMR, because proton 4 and 6 supposed to be chemically equivalent, because both are falling for the NO2 region with having same chemical environment, while H5 will show a separate signal and H2 will show a separate signal. So this type of proton NMR we can assume for the metadinitrobenzene. But here we are talking about homonuclear COSY. On the y-axis also you will have the same, and this is the two-dimensional NMR. We have diagonal peaks here and cross diagonal. Now based on, since we take out the coupling information, which proton is coupling to which proton here, so that information we'll get from here. In this you can see we are getting one contour below H4 and H6, and while meeting, it is meeting up with the another contour called H5. It means the H4, H6 protons are coupling with H5 signal. You are getting the cross peak for these two. So it means this H4 and H6 is going to split the H5 proton as a triplet. So you can see here you are having a triplet for H5, and H4 and H6 is going to split as a doublet because of this one proton here. So you are having doublet, and again it is splitted as a weak coupling. You can see doublet. So doublet of doublet we call it. Why it is so? You can see that this H4 and H6 is also coupling with the H2 proton. You can see the cross peak, one for H4, H6, another is for H2. It means these two are coupling with each other. So you can see here H4 and H6 is having a meta coupling or double coupling with H2, which is a weak coupling, and therefore you can see the slight splitting of the strong ortho coupling or 3-bond coupling with respect to H5. So in that way we can find out the coupling information about the beta-dinitrobenzene for this by using the 2D NMR. So if you get this question theoretically, for M.Sc students, you can draw the 2D dimensional NMR, homo and heteronuclear COSY. Take these examples and explain your answer. The last technique is chemically induced dynamic nuclear polarization, called CIDNP. Chemically induced means we are talking about a chemical reaction. Nuclear polarization occurs. So basically this effect is detected in proton NMR spectroscopy. You may get here absorption signals or emission signals as a negative peak. And this effect basically will arise when you have unpaired electrons or radicals, which is generated during the chemical reaction. So this proves that the reaction is going through the radical formation. So let's take this example where you have dipropanol peroxide, which is either thermally or photochemically will dissociate into free radical. Further dissociation will occur and will form the ethyl free radical, which is captured by thiophenol, and it will form the thiophenitol. So if you record the CIDNP spectrum, we will see that how does it looks like. And this technique is basically very good evidence that for the reaction goes through with the radical mechanism, because you will get the spectrum for the radicals involvement. So this is basically the CIDNP spectrum for the ethyl portion of the phenitol. You have CH3 and CH2. You can see ethyl phenitol. So if you see the normal spectrum, the ethyl will give you a triplet because of the neighboring 2 proton, and the CH3 will give this CH2 will give you a quadrate because of the neighboring proton, 3 proton, 3 plus 1. So this is the normal spectrum proton NMR, and if you just compare the CIDNP, you can see here you have the absorption peak, you have the emission peak here. The peak just above triplet belongs to the CH3 here, and this is for CH2. CIDNP. The advantage here is basically what is the significance, that the nuclear spins in this product of this radical reactions are undergoing polarization because of the chemical reaction. that is producing the molecule. So this is a proof, the CIDNP is a proof that the radical reaction is going through. The mechanism is radical mechanism, and basically this particular technique is extensively used for the formation and decomposition of diaryl methanes, triethyl methanes and acyl peroxide nowadays. So this is about CIDNP mechanism, a technique basically used to identify that the mechanism is through radical, and many applications are there nowadays. So hopefully you have understood all the three techniques called NOE, COSY and CIDNP. All the best for your exams. Happy learning.